All right, let's finish up section 1.8, direct products and so forth. We left off just before theorem 1.8.6. So following result gives conditions under which a group is isomorphic to a weak direct product of a family of its subgroups. And notice in this case, we've added a hypothesis of normality for these subgroups. So the statement is, let N sub I be a family of normal subgroups of a group G, such that G is generated by the union of those normal subgroups for each K in the indexing set capital I, subgroup N sub K intersect the group generated by the union of all of the other normal subgroups only consists of the identity. So these subgroups are big time practically disjoint. Of course, they have to share the identity because they're all subgroups of a given group G and they're groups themselves. So they have to share the identity. So the overlap between them is really minimal in a sense. With those two hypotheses satisfied, the claim is that G is isomorphic to this weak direct product of the N sub i's. So let's look at a proof of that. Let's proof of that, wrong spot. Okay. All right, it's an isomorphism claim. We'll construct an isomorphism. Okay, so let's take ourselves an element, a tuple, as I like calling it, of this weak direct product. Then we know what that means is a bunch of these A sub i's equals the identity. Now, everything's happening inside group G. In this example, the N sub i's are subgroups of group G. So there's only one identity, so we don't get the subscripted identities as we did before. So we can simply say being in this weak direct product means A sub I equals the identity for all but finitely many values of the index. As we did before, let's let capital I sub 0 be the set of indices for which the A sub i's are not the identity. So it's a little subset of indexing set capital I. It's a finite set because of the fact that we're considering a weak direct product here. If we take a product of the A sub i's as I ranges over this indexing set capital I sub 0, the claim is this is a well-defined element of G. First off, it's a product, just a regular old product in a multiplicative group, G, of the elements A sub I, as I ranges over capital I sub 0. It's a product of a finite number of things, okay, because infinite products don't make sense unless we got more structure than just a group. Binary operations only work, in a sense, as finite number at a time, unless we have additional structure and talk about convergence or something like that. But it's a finite product. So we got that going for us. My next concern would be, does the order matter? Because this set capital I could have been so huge, I might not be able to order it in a usual sense that we'd order, say, natural numbers, right? It might not be a countable set for one thing. But my concerns are over commutativity and order. But we've got, if we choose, say, an element A from N sub I and an element B from N sub J, two of these different normal subgroups, remember these normal subgroups only intersect in an identity, then in that setting, AB equals BA. We have commutativity of elements of A with elements of B in this setting. That's given by theorem 1.5.3 part 4. Why don't we take a look at that? Let's jump back to the notes, 1.5. Here we go. Here's what theorem 1.5.3 said. The setting for part 4 is G is a group, K and N are subgroups. N is a normal subgroup of G, and so is K, stated in 2 different places, but K and N are both normal subgroups of G. They intersect only at the identity. Then the claim is N times K equals K times N for any element lowercase k of subgroup capital K and any element lowercase n of subgroup capital N. And that's exactly what we have, and that's probably why we took that as hypotheses. It gives us this commutativity stuff between these normal subgroups. Within the normal subgroups, I don't know, between the normal subgroups, we get this type of commutativity. So we're not necessarily in a billion groups by any means. All right. So order doesn't matter because these A sub i's, they come from different N sub i's. So we can rearrange the A sub i's into any particular order that we want in this little finite product. So in that sense, we have a well-defined element of group G. So let's define phi mapping the weak direct product of the N sub i's into G as phi takes a tuple A sub I from the weak direct product and produces in G the product of the non-identity elements of this tuple, as we just discussed. So the capital I sub 0 just allows us to pick off the non-identity elements. I'd worry about order, but we've taken care of that. So this product is well defined. That is independent of the order in which you do it. So we'll take that as a mapping. We're trying to establish an isomorphism claim. So off we go, homomorphism onto and one-to-one. So we need to show it's a bijective homomorphism. So here's the definition of our mapping given here. Big time taking advantage that we're dealing with a weak direct product with all this finite stuff that's arisen. All right. First, take a couple of elements, tuples, let me call them. The tuples A sub I and B sub I from this weak direct product. Let I sub 0 be as above. That is, capital I sub 0 is the set of indices for which the A sub i's are not the identity. Similarly, define capital I sub 1 to be the set of indices for which the B sub i's are not the identity. So if we look at the union, I0 union I1, that's the indices for which either A sub I is not the identity or B sub I is not the identity. Both of these are finite sets because we're in a weak direct product. So the union of those two sets is finite as well. So it looks like we're taking a product over here. That makes sense. So take phi of the two tuples. We're trying to show that equals phi of the first tuple times phi of the second tuple. Remember, the tuples are elements of the weak direct product. How do you multiply tuples together in any kind of direct product? Component-wise. So tuple times tuple yields tuple, where the ith component, if you will, is the product of this ith component with that ith component. So we get the tuple with components A sub I, B sub I. What does phi do to that? It takes a product of all of these things which are not the identity. There's only finitely many of these things which are not the identity. I can tell you maybe which ones they are. All of the non-identity elements of this tuple have an index in this set. There might be a handful of identities in that tuple as well, but anyhow, all of the non-identities here are included in this collection of indices, I sub 0 union I sub 1. So what does phi do to such a thing? It gives us a product of the non-identity elements. All right, there you go. Like I said, some identities may have snuck in, but that doesn't affect the product. A finite number of identities. So we need the finiteness or it doesn't make sense in a group. we had that commutativity thing that we observed above. So I can move the A's. When I write this product out, we've got something of the form A1, B1, A2, B2, and so forth. I don't want to think of the subscripts as 1, 2, or whatever, but something of that sort. We know we can do the commutativity and collect the A's together on one side and the B's together on the other side, due to this idea of coming from different subscripted normal subgroups, that Theorem 5, 1.5 thing that we looked up. So commutativity allows us to collect the A's on one side, the B's on the other. Hey, over here, whenever I choose an index from I sub 0, we're not getting an identity. When I choose an index from I sub 1, maybe identity, maybe not. Did I say that correctly? Not the identity when we choose I from capital I sub 0. I sub 1, I don't really care. We can drop the I sub 1 from the union. So when I take a product of these, maybe some of the indices from I sub 1 include identities. Well, drop those. Similarly over here, some of the indices, now this time from I sub 0, may include identities for the B's. Drop them if necessary, and produce simply a product over I1. So we get equality there. If we've dropped anything, we've dropped identities. Hey, this is a product of all of the non-identity elements of this tuple. That's how we define phi of that tuple. So phi of tuple A sub I is this product. Similarly, phi of tuple B sub I is this product. That gives us the product of the phis. It's a homomorphism. Okay, so this mapping is a homomorphism. We want to show it's an isomorphism. So next, so we'll make an observation first. Next, let's make this following little observation. Then we'll take care of onto-ness, surjectivity, and then we'll take care of one-to-oneness, injectivity. For any A sub k and N sub k, consider the following. Take this phi that we've defined and look at the canonical injection iota sub k applied to A sub k. So remember what that does. That'll take this A sub k, produce a tuple, the kth entry of which is A sub k, and all of the other entries of which are identities. So we get a tuple out. It's in the weak direct product because all of its entries are identities except the kth entry, which is A sub k. That's what iota sub k does to things. It creates cardinality of I tuples, and it plugs into one position, whatever we've input over here. So that's what iota sub k does to A sub k. Phi acts on the tuples by taking a product of all non-identity elements of this tuple. So that'd be a product over everything that's not the identity. There's only one thing that's not the identity because we created this with a canonical injection. And that's the kth entry, which is A sub k. So we get the product of A sub k, end of story. We simply get A sub k out. So more generally in terms of index I instead of k, we get phi composed with iota sub I of A sub I equals A sub I. Simply how the mappings interact. All right, this identity we'll use in the following computations. Onto. Okay, G is generated by the subgroups, capital N sub I, part of the hypotheses. Every element A of G then is a finite product of elements from these N sub I's. Theorem 1.2.8 said, if I have a group generated by a set of elements, then the elements of that group are equal to products of powers of elements of the sets. Well, here we get products of powers of elements of these subgroups. But a power of an element of a subgroup is an element of a subgroup itself, so I can ignore the exponent stuff and say we just get a product of elements of the N sub I's. Also, we've got this commutativity behavior between these normal subgroups given by that theorem from section 1.5. So what we can do is write A then as a product of these A sub i's. I can sort of segregate the A sub i's that come from different subgroups. I can rearrange the orders as needed. So we can express this element A as a product of A sub i's over some finite subset, I sub 0. In a group, and in that theorem 1.2.8, we had a finite product of things. So we've certainly got a finite number of these A sub i's, and we've used the commutativity and the group properties to simplify it a bit over what theorem 1.2.8 states, and actually simply get a product of the A sub i's. You can list them in any order you want. You know they commute because they come from different normal subgroups. So we have some finite set I sub 0. We've started here taking an arbitrary element of G. So this I sub 0 is valid for this particular choice of element A from the group, not to be confused with maybe some of the things we were doing before. It's the same idea. But this I sub 0 applying to this element A. So we've got A, arbitrary element of G, written in this form. We want to show this is the image of something. And if you'll recall how phi maps things, you can probably figure out what the something it is that phi will map to this element A, knowing it can be expressed like that. So A is this particular product over set I sub 0, equation asterisk. So we'll refer back to this shortly. If we consider the product of all over all indices I and I sub 0, the set we just introduced, of iota sub I, A sub I, well, it's just a finite product of elements. We can only take finite products of elements. I mean, we've taken some wild direct products of sets. Might not even be countable, but when it comes to binary operations of elements, which is what we're doing here, that has to be finite. That's why you keep seeing these little subscripted capital I index sets popping up. So take a product over all I and that I sub 0, iota sub I, A sub I. Remember, iota is the canonical injection. That'll take this A sub I and stick it in this weak direct product. It will produce a cardinality of I tuple that's all identities except in position I, and in position I, it has entry A sub I. If we'll take a product of a bunch of those things, we get something in the weak direct product. You'll have for each individual thing all identities except for one position. So we do get, when we multiply the finite product out, we get exactly something in here. The number of non-identity entries is still finite. So let's apply phi to that thing. When you do, we're going to get exactly what we had at the previous, on the previous page. So phi of the product of these things here. By the way, this is something in the weak direct product. It's the something that's going to be mapped to element A. Phi of a finite product, homomorphism property, that's the product of the phi ofs. Homomorphisms preserve binary operations. We're using all this product stuff, so we're using multiplicative notation within these groups. So phi of the product is the product of the phis, if you will. Hey, we just saw that phi composed with iota sub I of A sub I is A sub I. That was a little side comment that we made. So we can replace this with A sub I. This we had shown on the previous slide. And by that start equation from the previous slide, that's A itself. So what we've shown is if we pick A, an arbitrary element of G, it's the image of something under phi. Actually, we found constructively exactly what it is the image of. It's the image of that thing there. So every element of G is the image of something in the weak direct product. So that mapping phi of the weak direct product into group G is actually an onto mapping. Everything A is the image of something under phi. Here's the something that corresponds to A. So now all we need is one-to-oneness. Let's use our usual way of showing a homomorphism as one-to-one. Let's show the kernel is trivial. The kernel only consists of an identity element. So to show one-to-oneness, suppose something in the weak direct product, the tuple, A sub I, suppose phi maps that tuple to the identity. You know phi maps that tuple to a product of its non-identity components, of which there's a finite number because we're dealing with a weak direct product. So introduce set capital I sub 0 as above. So phi maps the tuple into this product. Say that gives us the identity. So what we're saying here is this tuple is in the kernel of phi. It's mapped to the identity. Let's switch notation a little bit without loss of generality. Suppose this finite set I sub 0 is the indices we'll denote 1, 2, up through n. So I've got specific indices we can deal with. There's a finite number of them. You can call them whatever you want. Let's use these symbols. Then when we take the product over I and index and capital I sub 0 of these A sub i's, we get, in any order you like, A1 times A2 up through A sub n. And we know that's been required to equal the identity because we're dealing with something in the kernel of phi. You want to write these in a different order? Not a problem, because these A's came from different normal subgroups and you have that commutativity property. But I can use any order I want. Let's use the natural one. Well, if we have A1 times A2 up through A sub n equals the identity, we could multiply on the left both sides of this equation by A1 inverse and produce the equation A1 inverse equals A2, A3 up through A sub n. But A1 inverse, that's in normal subgroup n sub 1. A sub 1 was in n sub 1, so A sub 1 inverse is also in n sub 1. These things here, A2 through A sub n, well, that's an element of the group generated by the normal subgroups n sub 2, n sub 3, up through n sub lowercase n. All of the finite collection except for n sub 1. But the only thing that's common to n sub 1 in the group generated by these others is the identity. So that means A sub 1 inverse must be the identity, and this thing here also must be the identity. So this original product we had, actually we must have had A1 equals the identity if we had something in the kernel. And now we can deal with the equation A2 times A3 up through A sub n equals the identity. Same thing we had here, except the A1's gone. We'll use the same process, get rid of the A2, iterate that process, and inductively, you'll draw the conclusion that A sub I equals the identity for all finite number of these little A sub i's. So when we took this thing here, actually all of its components must have been identities, or the identity, since we're in a single group G. This must have been the cardinality of I tuple of all identities. That is, it must have been the identity in the weak direct product in here. So the kernel of phi consists only of the tuple, right? I'm using set brackets to indicate a tuple, the tuple of identities. And of course, we brought this up because we know by a very early result on homomorphisms, if the kernel consists only of the identity element, then you got yourself a one-to-one mapping, you've got yourself an injection. So we've shown phi is a one-to-one and onto homomorphism. I feel like you're more commonly algebraic terms, it's an injective, surjective homomorphism. It's an isomorphism. So we have that G is isomorphic to the weak direct product. Back to the notes. A corollary. Corollary to this is this case where we simply had a little finite collection of normal subgroups. Suppose N1 through N sub R are normal subgroups of group G, such that G equals N1, N2, up through N sub R. This is the group generated by N1 union N2, blah, 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 up through N sub R. Since these are normal subgroups, we have something to back us up on that. And we're requiring that we have the intersection property that we had above. Normal subgroup N sub K intersect all the others. Group generated by all the others is only the identity. That's exactly what we had here, the little angle brackets meaning group generated by. Then we get G is isomorphic to the direct product N1 times N2 up through N sub R. So when we take normal subgroups that intersect in a minimalist way, only at the identity, then the group we're dealing with is isomorphic to a direct product of those normal subgroups, provided they generate group G. This follows from the previous result simply by observing that the group generated by the union is this product thing that we had expressed. We dealt with that in theorem 1.5.3, so that's the only detail to worry about. Excuse me, we dealt with that in theorem 1.5.3 plus induction. This is 1.5.3. Of this part. So let's see, we're getting the fact that these products actually are groups, right? And we've assumed that they generate group G, but we do get that these products represent groups. We expressed it in terms of two normal subgroups here. And we've got, well, a finite number here. So that's why we need the induction. In fact, this corollary sometimes is called a recognition theorem. Let's jump forward to some notes. This is some supplemental notes I have to chapter 2 of Hungerford on semi-direct products. This is based on Dummett and Foote's book. I think it's simply called Algebra or Abstract Algebra. But Dummett and Foote, chapter 5, section 9, it's a little my notation for how they deal with things. They state the following recognition theorem. It's the same as what we just stated, it turns out, when we got two groups. It says, suppose G is a group with subgroups H and K, such that H and K are normal in G. H and K intersect only at the identity, slightly different notation, but I mean the identity here. Then the claim is the group HK equals, we'll talk more about this. I would go with isomorphic. Dummett and Foote may be doing things slightly differently. But the group generated by the set HK equals, well, isomorphic to the direct product of H and K. So this is exactly what we had in this result when R equals 2. So same thing. Time permitting, and we go through that section of Dummett and Foote on direct products and semi-direct products. Part of the puzzle is to go through and recognize when you're dealing with a direct product or a semi-direct product. All right. So let's build up some more vocabulary. Definition 1.8.8 says, okay, we're shifting gears a little bit here and giving normal subgroups more attention. Let N sub I in an indexing set, be a family of normal subgroups of a group G, such that G is generated by the union of those subgroups. And for each index, K and I, we have that N sub K intersect the group generated by all of the other normal subgroups is only the identity. So this is set up quite similar to what we just had. A bunch of normal subgroups that generate a big group G. And the normal subgroups intersect in a minimalist way, as I was saying. They have to intersect in at least the identity. We're requiring they intersect in nothing more than the identity. That'll get the commutativity stuff. Then G is called an internal weak direct product of the family N sub I, also called an internal direct sum if we treat these as additive groups and abelian groups, additive abelian groups. We'll stick mostly with the multiplicative notation, and we'll be speaking of internal weak direct products for most of the rest of the section. I want to go on about terminology. We had an external direct product and an internal direct product. More of that shortly, but here we're using internal. Quick comment about that. Everything happens in terms of group G. It's G we're defining to be an internal weak direct product. When we had external weak direct products, we didn't have an umbrella group, as I call it, under which things were happening. Here we do. So internal to what? These things are internal to group G. All these normal subgroups, or all these normal groups, are themselves subgroups of group G. They're internal to G. Another bit of terminology. If we compare multiplicative groups to additive groups, we have the following sort of correspondences. The terms direct product and complete direct sum corresponded when we first defined direct product. We said, here's a direct product of a bunch of graphs if they're multiplicative. If they're additive, sorry, a bunch of groups. If they're additive groups, then we called it a complete direct sum. Internal weak direct product and internal direct sum, as we just used here, correspond from the multiplicative setting to the additive setting. So I say, notice this funny use of the word complete in the sum setting and the word weak in the multiplicative setting. They both mean the same thing. They'll be ultimately there'll be something related to all but a finite number of things being the identity. That's not clear from what's been stated so far, but we got some more things to demonstrate. As a consequence, we don't refer to complete products and we don't refer to weak sums. It was the other way around. It was complete sums and weak products, just to try to get a grasp of this exotic terminology. When we speak of an internal weak direct product, by definition, we're dealing with these N sub i's as normal subgroups of G. When dealing with an internal weak direct product of a finite number of groups, this is something that'll pop up in the future in section 2.3, we'll use a particular notation that's not in Hungerford. Hungerford at some point soon is not going to distinguish between internal and external weak direct products, or as appropriate direct sums. I say if G is an internal direct product of normal subgroups N sub 1 through capital N sub n, we write, we as me, because I made this up, I'm going to write G as N sub 1 internal direct product with N sub 2 internal direct product, and so forth. So I'm using a little superscript on the product symbol to indicate it's an internal direct product. Notice also I've got an equal sign here, like Dummett and Foote had in their recognition theorem, in fact. So I suspect they're doing something like this. With this notation, there's a difference between the direct product of H and K and the internal direct product of H and K. The elements of direct product of H and K is ordered pairs. Yeah. An element of H, comma, an element of K. But the elements with the internal direct product are simply elements of group G, where H and K are normal subgroups of group G. That's a difference. Granted, a subtle difference, but over here you get ordered pairs and over here you get elements of G. Now it's going to turn out these two things are isomorphic, but they're different things. They're not equal, they're isomorphic. So, more of that before we're done here. We get the following as a classification of internal direct products. So we're taking a family of normal subgroups of a given group G. Everything is internal to group G. G is the internal weak direct product of this family if and only if every non-identity element of G is a unique product, AI sub 1, AI sub 2, up through AI sub n, with the indices distinct and none of the subscripted A's the identity. The subscripted A's coming from the obvious place, the corresponding subscripted capital N's. So every element of G, if every element of G can be written in this form uniquely, then we've got an internal weak direct product. So I see a lot of stuff with finite products. I don't specifically see the finite tuples exactly, our traditional use of the term weak. Also, the uniqueness idea is the reason we have to disallow the use of identities. And if I can throw identities in there, then I can use a different number of indices and so forth. So that's the reason, the only reason really for disallowing the identity. Proof of that left as an exercise, as they say. Another observation, rather similar to that, exercise 11, also gives a necessary and sufficient condition for G to be an internal weak direct product. These things I'd also call recognition theorems, and this is consistent with the idea of a recognition theorem, but that's terminology from a different book. These things fall in that category now. Let N sub I be a family of subgroups of a group G, then G is the internal weak direct product of these subgroups if and only if A sub I, A sub J equals A sub J, A sub I for all different I and J, A sub I and A sub J coming from the usual place. And every non-identity element of G is uniquely a product, AI sub 1 through AI sub n, with distinct indices, and we haven't used the identity. And what's disappeared in both of these, let's see, in particular this second one, let's concentrate on this exercise. There's nothing in there about intersections being the identity. And we use the intersections equals the identity stuff to get the commutativity. This explicitly gives us the commutativity here. So commutativity played a big role in these internal weak direct products. And we've got that apparently, according to this exercise, if we have a weak direct product and conversely. And here we go. Here's some more stuff, and I want to illustrate it with an example. Distinguishing between internal and external weak direct products. For G, an internal weak direct product of groups N sub I, we have, by definition, each N sub I is a subgroup of G, and G is isomorphic to the external direct product of those N sub I's. Theorem 1.8.6 gave us exactly that. We went through and established the isomorphism. So, strictly speaking, we're not getting G equal to this weak direct product. We're getting it isomorphic to this weak direct product. But I do have the N sub I's specifically as subgroups of group G. That's what the definition said. Now, if we look at an external direct product, external direct products don't contain these N sub I's, but contains isomorphic copies of them. So in one place, I get the isomorphism on the big group G. In the other place, I get the isomorphic term on the little constituent groups N sub I. Remember, elements of a weak direct product are, my trademark term here, cardinality of I tuples. the cardinality of I tuples with each entry the identity, except the ith entries ranging over the elements of n sub I form these subgroups of the weak direct product, which are isomorphic to n sub I. So for internal weak direct product, n sub i's are subgroups and G is isomorphic to the weak direct product. For regular old weak direct products, if we take G to equal this, say, then we don't get the n sub i's as subgroups, but we get subgroups that are isomorphic to the n sub i's. So in one place you got an equals to and an isomorphism, and in the other place you've got an isomorphism and an equals to, and in some sense they interchange roles. And I can explicitly tell you what those subgroups are. Yeah, and in the ith component you got in there, you got that subgroup n sub I. Well, actually in here, the elements are cardinality of I tuples, so you have to take that subgroup, in a sense, it's surrounded by identities. Identities everywhere except for in the ith component is what the statement means in this second to the last line. Let's illustrate that a little more explicitly with an example. And this is just me going on. Hungerford just washes over the whole thing. And doesn't get into internal versus external direct products. It says they're isomorphic, so I won't bother. But I'm a slow learner, so let's go through some of this in detail. Consider the integers mod 6. Certainly the integers mod 6 are isomorphic to the integers mod 2 plus. So here we're dealing with an external direct sum plus, let me read it as z2 plus z3. Now, we've got three little finite cyclic groups here. Let's denote the elements of Z2 as 0 bar sub 2, 1 bar sub 2. The elements of Z3 is 0 bar sub 3, 1 bar sub 3, 2 bar sub 3, and Z sub 6 as 0 bar sub 6 through 5 bar sub 6. So I've introduced the subscripts to indicate how the arithmetic's done. I leave the subscripts off and I can't tell the difference in this 0 bar, that 0 bar, and that 0 bar. And they're different because they come from different groups. So these Z2, Z3, Z6, those are all three different groups. So I don't want to use the same symbol, so I put the subscript on there. When I say 1 bar plus 1 bar equals what? Well, you can't tell unless you know if it's the 1 bar from here. Here, 1 bar plus 1 bar equals 0 bar. Here, 1 bar plus 1 bar equals 2 bar. Same thing over here. So the subscripts make explicit what these equivalence classes represent. Let's look at this external direct sum. Z2 plus Z3. Okay, that'd be ordered pairs. We'd have all possible ordered pairs where the first entry is an element of Z2 and the second entry is an element of Z3. 2 choices for first entries, 3 choices for second entries. That's a total of 6 things. There's the 6 ordered pairs. We can define a mapping from Z6 into these ordered pairs that is an isomorphism. So certainly these are isomorphic. It's easily confirmed. Here's the confirmation. We'll have to map the identity to the identity and maybe play with it a little bit. I leave the details to you, as it's straightforward, to confirm this really is an isomorphism. But here's how we'd map the 6 elements of Z6 to the 6 elements of this external direct sum. But they're different things. Z6 has, in a sense, just elements, whereas the external direct sum has ordered pairs of elements as given. So they're different. They're isomorphic, but they're different. The elements aren't even the same, just regular old equivalence classes, mod 6 here, and in ordered pairs is described. So if we want to write Z6 as an internal direct product, we'll have to start with subgroups. Normal subgroups, not a problem. We're in an abelian setting, so all the subgroups will be normal. So we need 2 normal subgroups of Z6, one of order 2 and one of order 3. Here they are. Let H be 0 bar sub 6, 3 bar sub 6. That's a subgroup of Z6 of order 2. 0, 2, and 4 bar sub 6. There's a subgroup of order 3. So these are subgroups of Z6. We're doing the internal thing. So they're internal to what? They're internal to Z6. And if we look at the group, subgroup of Z6 generated by H union K, union them, we get 0, 2, 3, and 4. That set of elements, take the set of elements generated by that. We got everything in Z6 except for 1 and 5. We can produce 1 and 5 by adding 1 bar sub 6 and 5 bar sub 6. But we can generate the 1, for example, by adding 3 and 4. 3 plus 4 mod 6 is 1. So that's how you get the equivalence classes given here. We need 5 as well. That's easy. The equivalence class containing 5 is the equivalence class containing 2 plus the equivalence class containing 3. So when we look at the group generated by these, it generates all of Z6. So in my notation, with a little superscript on the multiplication sign, I'd say Z6 equals the internal direct product of H and K, whereas Z6 doesn't equal the external direct product of a group of order 2 and a group of order 3. We pick up this isomorphism. So we get an isomorphism when I deal with external direct products versus an equality if I'll treat these as internal direct products. Here, the group of order 2 and the group of order 3, there they are. They're subgroups of Z6. Up top, they're not. Z2 is not a subgroup of Z6. Z6 has a subgroup isomorphic to Z2, and it has a subgroup isomorphic to Z3. In fact, here they are respectively. So there's a subtle difference on internal and external. Hungerford uses this notation for an external weak direct product, but he doesn't give us a special notation for an internal weak direct product. In fact, he says, and I'm going to stubbornly hang on to my distinction as long as I can, but when reading the book, he doesn't distinguish between internal and external. Page 66, Hungerford states, practically speaking, this distinction is not very important, and the adjectives, internal and external, will be omitted whenever no confusion is possible. Like I said, I'm pretty easily confused, so I'm going to try to distinguish between the two in the notes and in the videos. He then says that we simply use a notation for an external direct product to represent both external and internal direct products as given here. I'll be a little bit more careful than that, though, especially when we encounter this again in somewhere in chapter 2. All right, let's look at some other, in my opinion, kind of oddball behavior here. One of the exercises, one I made up, 1.8.b, it's got a letter after it. It's one I've found somewhere, made up. You're asked to prove that if G equals the direct product of H and K, then K is not a normal subgroup of G, neither is H, because H and K aren't subgroups of G, but they're isomorphic to some subgroups of G. If we'll take the subgroup identity element of H, so taking the trivial subgroup of H, direct product of that with K, okay, that's the right thing to be a subgroup of H direct product K, because it's a direct product of a subgroup of H and a subgroup of K, K itself. Claim is, this is a normal subgroup of G. So I'm not saying K is a normal subgroup of H times K. I'm saying this thing here, which is isomorphic to K, is a normal subgroup of G. If it's a normal subgroup, we can take quotient groups. In fact, if we'll take G mod this normal subgroup, that is, if we take H times K, that's what G was, H times K, mod this subgroup that's isomorphic to K, we get out something that's isomorphic to H. That's suggestive. We'll deal with this more before we're done as well. And similarly, we can take H times the little subgroup of K, consisting only of the identity. This is also a normal subgroup of G. If we'll look at the quotient group H times K mod K times that little trivial subgroup, you'll get something isomorphic to K. It's looking like we're dealing with quotients and doing some cancellation. But I'll give some pretty explicit warnings before the section's out that that's not how quotient groups behave. But if G is an external direct product of H and K, then H and K are isomorphic to normal subgroups of G. Yeah, we got this thing here. That's not K itself because its elements are ordered pairs. The second entry in those ordered pairs are elements of K. But of course, it's isomorphic to K itself. All we've done is taken the group K, turned it into ordered pairs by putting in the first entry of that ordered pair the identity of group H, and then kept the elements of K ranging over those elements for the second entry. So we're stuck with this thing about isomorphic to a normal subgroup, but not equal to a normal subgroup. If G is an internal direct product of H and K, as expressed here, then H and K are normal subgroups. Whenever you had an internal direct product, these things here gave you normal subgroups, part of the definition. In exercise 1.8.c, another exercise I made up to deal with this internal versus external stuff that's come up here. You're asked to prove that if G is the internal direct product of normal subgroups n sub 1 and n sub 2, that is if G equals n sub 1, internal direct product with n sub 2, then G is isomorphic to n1, direct product to n2. And conversely, if G is isomorphic to direct product, then there's normal subgroups, n1 and n2, n1 isomorphic to H and n2 isomorphic to K, as it says down here. And then G equals the internal direct product of those normal subgroups. So anyhow, that's the difference in internal and external. It's whether you're dealing with groups as direct products or groups that are isomorphic to direct products. Normal subgroups or subgroups that are isomorphic to, normal subgroups, H and K, or things that are isomorphic to these types of normal subgroups. And it's all a matter of direct product or indirect product, equals or isomorphism. So all this stuff, and even more generally, if we had more than two, this conversation's been about two internal direct products or just direct products of two groups. But in general, if we had arbitrary weak products, all this stuff can be whitewashed, is my term, with a blanket isomorphism comment up to isomorphism. And that's why Hungerford's taken the approach that he's taken.